Bismillahirrahmanirrahim. So today we will discuss on the network theorems. There are a lot of theorems which are used to solve the complicated networks, and you know that the how to solve a circuit by using the KCL and KVL. That means KCL and KVL, or we can say in general the nodal analysis and the mesh analysis. By using nodal analysis and the mesh analysis, we can solve any circuits. But however, you have to put a lot of effort in solving a complicated circuit by using the nodal and mesh analysis. So we will talk about something known as network theorems. There are many network theorems. We will discuss all of them, inshallah, if possible. So a lot of network theorems are there. And what is the use of these theorems? Actually, it is used to solve the complicated networks. Suppose you have a very complicated networks and you are interested in finding the current or voltage to a particular component, maybe a particular branch, not all the part of the network. You will be having a for you can assume you have a very complicated network which contains hundreds of resistors, hundreds of capacitors, hundreds of inductors, many things. And suppose you are interested to find a current or the voltage across the inductor or a capacitor or a single element. Just you are interested only in a single element. In such a case, solving the whole complicated network is a difficult thing. Actually, you don't want that. So in such cases, usually the network theorems are used. So if you have a complicated network, so we will be talking about, from today onwards, we will talk about the network theorems. Okay, these are the theorems which are developed for
theorem, Doctor.
I think there are some 6 to 7, okay, 10 theorems are there, I think so. Anyway, inshallah, we will discuss them all. I cannot count them everything. You have one theorem which is known as superposition theorem, and you will have something known as the Thevenin's and Norton's theorem. Then you have something known as the maximum power transfer theorem. You have something known as Millman's theorem. Like this, lot of theorems are there. Reciprocity theorem. Anyway, a lot of things are there. Okay, inshallah, we will see all of them. Okay, so first of all, superposition, but you will see something. Yeah, you know something about superposition, but inshallah, we will see in more detail. Okay, so
Inshallah.
when do we use the theorem? First of all, you should understand, if you have a complicated network, if you have a complicated network, it's very complicated. That means you have a lot of resistance, capacitance, everything. Okay, so complicated network with several components. Okay, in this case, actually, you will use the theorem, and you are desired. That means if you have a very complicated networks, then only you will be using theorem. If you have very small network, you don't want the network theorems at all anyway. And if the response in a single, this is very important point, single element is desired, that means you want to find the current, voltage, power, or whatever, okay, across a single element. Maybe you have a very complicated network with hundreds of resistors, but you want to find only the current and voltage across a single element or a single resistance. In such case, actually using the network theorems. Okay, you can write like this: network theorems. In such case, we will use, or then the network theorems are used. Okay, now you know where to use this. You have a complicated network, so in this condition, actually you will be using the network theorem. Okay, you have a very complicated network and you want to find the current, voltage, or anything, something across a single component. In that case, actually, you will be using the network theorem. I hope that this is clear to you.
Yes, doctor.
So the first
Yes.
theorem, yes, the first one we are going to discuss is superposition theorem. Okay, superposition theorem. So we will use this in a linear network. In a linear network, okay. If the network is non-linear, if it is non-linear, if you have a non-linear component like a diode, for example, we have seen that. One example, you remember? So we have seen one example, I think. If you have a non-linear network, you cannot use it. So if you have a nonlinear network, you can use it, okay, with several components. Okay. In this case, you can use this, okay. Several components, or you can say several components, not several components, we can say several independent sources. Independent sources, okay. You have lot of sources, independent sources. So the response in a particular branch, okay, particular branch, you are just focusing only on a particular branch. For example, all the sources are acting simultaneously, okay. That means all the sources are acting together, actually. That is known as simultaneously. That means you have a lot of sources in a network and everything is acting together. So that is equal to the linear sum of individual responses calculated, okay, by treating one, that means independent one independent sorry, this is one independent source at a time, okay. This is known as the uh, superposition theorem. Excuse me one second, I have just a
Take it, doctor.
okay,
Okay.
Okay, no
excuse me.
problem.
Okay, can you hear me now? It's fine.
Yes, sir. Yes.
Yes, yes, sir.
Okay.
We hear you.
Okay, so in this case, that means you have a lot of sources acting together. That means you have a lot of independent sources which are acting together, and you want to find the total response of the system, or total current or a total voltage across a branch, just across a branch or something like that. So in such case, you can use the superposition theorem to solve it in a very simple manner. Okay, suppose you have a system with three sources. So all sources are acting together, maybe two current source and one voltage source. Now you have to find the current or voltage across a resistance. Now you will just turn on only one source and find the response. Then you will turn on the another source and find the response. Then you will turn on another source and find the response.
Doctor.
And you will add all this together. Okay. Yes,
Doctor,
yes,
if there
yes.
is dependent source in the network, we cannot apply this theorem.
Yes. I am coming to that point. Okay, I will explain it, inshallah. So you can see, now I talk only about the independent sources. So how to treat the independent sources? After that, I will come to the dependent source. Okay, you have to, if you have a ideal voltage source, if you have three voltage sources, you want to remove two voltage sources. Okay, you want to remove the other two sources, then what you have to do, if you have voltage source, how you can remove a voltage source? By
short circuit.
Yes, short circuit. If you have an ideal current source, what you have to do?
Open circuit.
Open circuit.
Yes, this is the basic idea you have to know. Okay, next I will explain about the features. Okay, the features of the theorem. Features. Okay, this theorem, the first features, it is applicable only to linear network, only to linear networks. Okay, this is very important point. If you have a non-linear element in the network, you cannot apply this. Should be careful about this point. Okay, that means you have the network with resistance, maybe inductor, capacitor, transformer, no problem. Okay, transformer, linear controlled sources, linear controlled dependent sources, you can say. In other words, you can say dependent sources. Okay, so even though if you have dependent sources, you can apply this theorem, but there are some conditions for the dependent sources. The dependent sources should be linear. Okay, what is this linear dependent sources? Can you tell me an example?
DC.
You have a voltage source like this, some constant, yes, some current Ix, for example, it is controlled by a current Ix in the network, but this is a linear dependent source. Okay, linear controlled source. Suppose you have another thing, you have something like k into Ix square. Is this linear or non-linear?
Non-linear.
Yeah,
Non-linear.
so this is non-linear. Yes, in this case you cannot apply the superposition theorem is not applicable. Okay, but here
If
superposition
it is
theorem, if you have a
AC
network,
source,
no problem at all. There is no problem with AC source or DC source. Okay,
but
so it
AC
is
source not linear, doctor.
why?
Because when it's not line, it can be take any shape. Maybe sinusoid, maybe square. Can
The
not.
network is linear. Network doesn't mean that the network is linear, means it is depending upon the input and the output. That I will come after some few minutes. Okay, inshallah, I will come to that point, inshallah. Okay, what is this linearity and non-linearity? Okay, suppose, and the second feature of this theorem is the presence of the dependent sources, the presence of dependent sources makes the network an active. Okay, this point is clear. If there is a dependent source in the network, actually it is an active element. A dependent source will be usually made by using the transistor. You know this point, right? And transistor is nothing but an active element. It is not a passive element. We know this thing. Is it clear? Yes. So
Okay.
yes, and hence, okay, the superposition theorem, I will use this SPT for superposition theorem. SPT is valid, okay, valid for both active, okay, active and passive. Okay, it was active for it can be applied for both active and passive networks. Okay, so I hope that this is clear to you. Okay, and while applying the theorem, you should be very careful. One more point here is very careful. While applying the theorem, do not disturb the dependent sources. If there is a dependent source in the network, don't do anything on it. Don't disturb it. Okay, so you can open circuit and short circuit the ideal voltage sources and ideal current sources, but the main point, do not disturb the dependent sources. Don't do anything on the dependent sources. Keep it as such. Is it clear?
Yes.
Yes.
Yes. So the superposition theorem can be applied for active networks as well as passive network. But the main point you have to be very careful is it is not applicable. It is not applicable to nonlinear sources or something like that, dependent sources, for example. Okay, if the nonlinear dependent sources, you have to find another theorem. Don't use superposition theorem. Okay, and what is this linearity? I have already explained it during the first lecture, you remember. Suppose you have a system, I told you, system, you have a system and you give an input x of t and you got an output y of t. Suppose you give an input x1 of t and you are getting an output y1 of t, and you give an input, another input x2 of t, and you may get another output y2 of t. And this input can be AC or DC. It can be a DC voltage like this, and it can be, or it can be an AC voltage like this. Input doesn't matter. Property of the system, not the signal. This is the signal actually, but we are talking about the property of the system. Okay, and this is the system. So if you give something like some a into x1 of t, suppose you give here let's say you have a sinusoidal voltage with amplitude 1, and you multiply this with a, this is x of t, x1 of t, and you multiply with a, then the amplitude become, maximum amplitude become a. So that's what a into x1 of t, then you will get a into y1 of t. If you multiply the input with b, then you will get output also multiplied with the b. And this is known as, this feature you can see here, this is known as the homogeneity. Homo means same. That means when input is multiplied with a number, output is also multiplied with the same number. That's why we are calling it as homo. In English, actually, homo means, you can say, it is same. Okay, the meaning is same. Now you combine these inputs. That means a into x1 of t plus b into x2 of t. Then you will get the output as a into y1 of t plus b into y2 of t. And this is actually is the linearity property, you can say. So it is obeying the linearity property. That's why it is known as superposition theorem. Superposition is the principle of homogeneity, and you can see this is the principle of additivity. That means addition. This is known as additivity. Okay, that means if you add the inputs, the output is also just, you can add it. Understood? Got it?
Sorry, yes, clear.
So
Doctor, that's the reason why it's not applicable in non-linear.
in nonlinear system, it is not applicable. Why? Because you see here, this is, I'm not talking about the superposition theorem. I am talking about the linear system. So in this linear system, only the superposition is applicable. That means SPT. So this is the linear system. This is the property of the linear system. SPT means superposition theorem is applicable only to linear system. Linear system. Okay. You got the point? What I'm saying?
Yes.
Yes,
Yes.
sir.
Yes. In nonlinear system, I can give you an example for nonlinear system if you have some system. Suppose you have a system which is equal to a into x1 of t plus, sorry, you have a system like this. You are giving an input, for example, x of t, then you are getting an output y of t. Y of t is defined like x square of t. That means it is squaring the input. Okay. Now you give x1 of t. Then what will be the output? y1 of t. How much?
X1 square.
x1 square of t. Yes. Now you give x2 of t. What will be the output?
X2
y2
square.
of t. Yes, x2 square of t. Now you give something known as, you combine the input, additivity. You multiply with a, no problem. You will get here a. You multiply with b, you will get here b. Yes, if you have something like a, like this. Now if you take x1 of t plus x2 of t, what will be the output? This is your x3 of t.
x1 square of t, x
Is it?
x2 square.
Are you sure? You have to, the input, this is your input, which is nothing but
Sir, y1
x3
will
of
be
t.
y1 will be a square x square.
What? Yes, a square x square. You see here, this is b and b square x square. That will be the case. So, thank you for this. Okay, I forgot to write it. Now if you give x3, and y3 will be equal to x3 of t the square. Is it okay? x3 of t the square. This is nothing but x1 of t plus x2 of t. You have to take the whole square. Okay. Now
Yes.
if you give x1 of t, you are getting the output x1 square. If you give if you give x2 of t, you are getting the output x2 of t. Okay. And if you add both this, what is the sum of this? This is nothing but y1 of t, and the another one is nothing but the y2 of t. If you add this x1 square of t plus x2 square of t, and you compare this it with x1 of t plus x2 of t, the whole square, is it equal? It is
No.
not same. That is non-linear. Okay,
Not equal.
non-linear. That's, yes, it's non-linear. So that is a non-linear system. Anyway, I'm not going to touch it because I cannot cover the important topic. That's a problem. Okay, so you understood what is a linear system. So it is applicable only to the linear system. Now let us consider our superposition theorem. Okay, you have a very complicated network. I am just representing it with a box. Okay, so SPT is applicable for the sorry, not SPT. I am talking about the homogeneity now, the homogeneity property. I told you about the homogeneity property just before. You can see this. This is the homogeneity property. If you give a into x1 of t, then you will get a into y1 of t. If you give b into x2 of t, you will get b into y2 of t. Okay, that is the homogeneity. It will be multiplying with the same factor. You have a network. Network means a network contains lot of voltage sources, lot of current sources, many things. Maybe it can be lot of inductor, capacitors, everything. You take one branch. This is one branch which is coming out of the network, one branch, and you have one voltage source, you know. Okay, and this is a network. It contains a lot of resistance, capacitance, inductor, many things maybe. And there is one branch. The current through that branch is 2 ampere, and the current through this input is 3 ampere, and you apply 10 volt. Okay, now can you tell me, same network, same network, you have the branch here, but I apply 40 volt, same network, I apply 40 volt here. What will be the current, and what will be the current here? This position, what is the current, and what is the current here?
I1 is 12.
Depending on the network.
I2 is
Their network is linear. Very, very important point. This is a linear network. What will be the current? First current, what will be the current here?
12
What will be the
ampere.
current here?
12 ampere.
It will be, yes, because you see here, this 40 is nothing but 40 is equal to, you have a 10 volt and you multiply with 4, right? So you can multiply this current also with 3 ampere, you can multiply with 4. And you have the old current 2 ampere, you can multiply with 4. So the current here, it will be equal to 8 ampere. And the current here, it will be equal to 12 ampere. Is it clear? You don't need to solve the network, but you should have an information that the network is linear. Okay, got it?
Okay.
Okay.
This is known as the homogeneity. This principle is known as homogeneity. It is possible only in linear network. In non-linear network, you have seen this. If I give you a into x1 of t, what happens? It has gone a square. Then that property is not valid in non-linear network. That's why the homogeneity. Now I will give an example again. You have a network like this, which is 3 ohm. Okay, you have something. This is a network 4 ohm, and this is 4 ohm, and like this. Okay, and this is 20 volt. Okay, suppose this current is 4 ampere. Okay, and this current is 2 ampere. Now you change this 20 volt to some 80 volt. What will be the current? 4 ampere will change to how much? 4 ampere.
16.
Yes, very good. It is 16 ampere now. Okay, and what happens to this current?
8.
8 ampere. Okay, this is known as the homogeneity principle. I hope that this is clear to you. Very clear, right? Homogeneity.
Yes, doctor.
This is possible only in linear network. Okay, linear network. This you see, without solving anything, you can find the current and the voltage. Okay, but it is very valid only for the linear network. Okay, now we will see some problems based on the superposition theorems. Okay, the first problem. So determine the current through the 3 volt source. I will give you the picture. Okay, and you have to use superposition theorem for this. You can solve it by using another methods also, but now here I am teaching just only we are discussing about the superposition theorem. This is a 3 volt source, and it is given this is a 4 ohm resistance, and there is a current source which is going like this, which is 0.25 ampere. So we have to apply the superposition theorem. Okay, we are going to apply the superposition theorem. So what should do first?
Start with the source.
Turn off one of the sources.
Yes, we will turn off one of the sources. You see here what we are doing here when we turn off one of the sources. We are just finding the response of x1 of t. Not here, not here. When we turn off one of the sources, just taking x1 of t. After that, we will find what is y1 of t. Then we will give the input x2 of t only. After that, we will find what is y2 of t. Then we will add these two, then you will get the total response. Is it clear?
Clear, sir.
Yes.
Yeah, and this is the definition actually. By definition of the linear system, this is the property. So superposition theorem is directly related to the definition of linear systems. Don't forget this, because whenever you have a linear system, it should obey the property of superposition and homogeneity. Okay, so it should obey the superposition and homogeneity. That is known as a linear system. So first of all, I remove the current sources. Remove the current source. All are independent sources here. So I remove the current source and I got a response. The question is to find the current through the 3 volt source. Now what is the response here? This is 4 ohm and this is 3 volt. Now you know what is the current. Very easy. 3 by 4.
0.75.
0.75 ampere. Now remove the voltage source. That means voltage source, how can remove? A voltage source is short circuit actually. Yes. Short circuit the voltage source like this. Then you have a 4 ohm resistance, and yes, this is 0.25 volt. Can you tell me what
will be zero?
The resistance will
what will
go.
be?
So
You
all
see
the
here
current
what is
will pass through the wire.
Very good.
Because the
Yes.
resistance is low.
Yes. So the current will be coming here, and you see what is the voltage across this point between these 2 points? It is 0 volt because short circuit. You understood? Since this is 0 volt, you can say the voltage across the voltage across the 4 ohm resistance is also 0 volt. So the current through the 4 ohm resistance will be equal to 0 ampere. So the current will be equal to 0 ampere, whatever be the direction. Okay. Yes. So all the current will be flowing here, and this current is 0.25. Okay. So we can say this current, first current is I1 and next current is I2. So our current I through 3 volt source will be equal to I1 plus I2, which is nothing but 0.75 plus 0.25, which is equal to
But
1 ampere. Yes.
Zero, doctor.
how can we say there is a 0.25 ampere through the voltage source while we removed it? How can it be?
We didn't remove it. We just find the individual response. We have shorted the point. We shorted the point. We want to remove this. We want to remove a voltage source means short circuit. Short circuit means voltage equal to 0. I will give you
There is no current.
I will give you the explanation. Okay, it will be clear to you. You have a linear system. Okay, and you have x1 of t and you got y1 of t, and you have x2 of t and you got y2 of t. Okay, now if you have x1 of t plus x2 of t, you are getting y1 of t plus y2 of t. Now suppose you want to remove one of the sources. You take this equation. If you want to remove one of these sources, you want to remove this. What you have to put? Remove means what? It should be equal to 0. Am I correct?
0.
0. So voltage equal to 0. In the previous problem, voltage is equal to 0. What is this? Voltage is equal to 0 means you have the power supply. You are not going to remove this, but the voltage is equal to, I don't know what.
Zero.
Okay, voltage is equal to 0. Voltage is equal to 0 means it is a short circuit, simply short circuit. Am I correct?
Equal to 2.25.
Hmm?
Here
Yes.
in the equation, you write I2 equal to 0.25.
Yes, because you are finding this is only one source here. One source. And that source is the voltage source. And here only one source again. One source. And that source is the current source.
I think,
Okay.
Doctor, he means how it can be current without resistance.
Current?
Doctor, in the second case,
Yes.
I2.
Yes.
I mean I2.
Yes. Yes.
There is no current across 4
What-
ohm resistance.
No current through the 4 ohm resistance. What is the problem with that?
But you hear, doctor, you write 0.25. It is 0.
I didn't write 0. This is 0 ampere. You see here through the 4 ohm resistance. I have written 0 ampere. I2 is here.
In the
Current
equation,
through the other
doctor,
branch.
in the equation.
In the equation, which equation? I2 is 0.25.
Sorry, doctor. You find the you find the
Yes,
current
this
through
is
the
I2.
voltage source, not the 4 ohm.
Yes,
Yes.
this is the question. You see the question. Please see the question. The question is
Yes, I confused.
current through
I
3.
thought that
No, it is not. The question is not to find the current through the 4 ohm resistance. Okay. The question is to find the current through 3 volt source. Okay. It's clear.
yes. I got you, doctor. I got you. Clear.
Yes. Okay. I think the response of my tab is actually, it's very slow response. There is some issue. Okay. I will reconnect once again. Okay. It is very slow response.
Take your time, doctor.
Okay. I think you can see the screen now.
Yes.
Yes. So
No, doctor. The screen is not available.
No, doctor. I cannot see.
I can't see it.
it's very slow response. Determine. I think you can see now. Okay. Determine.
No,
I
I
don't know
Doctor, I
what has
cannot see.
happened. Okay. Determine the current. You cannot see anything?
No.
No, doctor.
No, doctor.
Okay. Excuse me. I will reconnect again. Okay.
Take your time.
أخبار الشباب؟
الله يسلمك ابو احمد، كيفك اخبارك؟
نحمد الله.
Yes, we can see now, doctor.
Yes, fine. I think you can hear me also. Fine. Okay.
Yes.
Okay. So we will see another question. Determine the current I. Okay, I will mark the I anyway. Determine the current I. So you have a current source like this 1 ampere current source, and this is 1 ohm resistance. There is 1 ohm resistance, another 1 ohm resistance, and you can see here, and there is 1 ohm resistance here. Okay. And you have given a power supply which is plus and minus here like this. This is 1 volt, and you want to find there is another branch which is connected like this, and this current is I. You want to find this I, and this is again 1 ohm resistance. Now, how to find this? We have to apply the
Bridge, doctor.
superposition theorem. It is a bridge anyway. First of all, we have to apply the superposition theorem. So for as indicated, apply superposition theorem. You can see, remove the 1 ampere current source. This one ampere current source. I'm going to remove this. So it is an open circuit, and it is an open circuit, and you can see if it is an open circuit, you can see 1 ohm. Again, this is 1 ohm. This is again 1 ohm. Okay. Now this is connected like this. You can say, is it okay? I draw like this. Is it any problem?
Okay, sir. Okay. No problem.
Okay, no.
Oh, okay. Now can you see something? Can you see something very interesting? I am talking about this I, not I. It is I1. Why I am saying I1? Because I removed one source. Okay, I will. Yeah, I'm finding the response only due to the voltage source. You can see you have a voltage source between these 2 points, plus minus. Okay.
Will be 0, doctor.
So I can draw this circuit in another. Very good, because the bridge is balanced. You can see here. I can draw like this. Okay, this is A, this is B. I can draw like this. This is A, this is B. Okay, now I can draw like this. Okay, and between A and B, I have a current. That means between A and B, a current like this. Sorry, I have a current. This is between A and B. I1, and another thing, another resistance. You have 1 ohm, 1 ohm. Is this same or not? Please observe carefully. Is it same or not?
Same.
Is it same?
How it could be like this,
Same.
Doctor?
Now you see here. Now you can see this resistance is 1 ohm and this is 1 ohm. So 1 ohm into 1 ohm, and if you take this guys, 2 guys, is equal to 1 ohm into 1 ohm. You can see the bridge is balanced. Then what will be the current I1? If the bridge is balanced, what will be the current I1?
Zero.
I forgot to write the voltage source here. I forgot to write the voltage source. The voltage source is 1 volt. You can see, you can apply between other two. You can say this is your voltage source is here. The voltage source. Now what will be the current I1? It will be equal to?
The current will be 0, Doctor.
Yes, very good. It is 0 ampere because it is balanced. Okay. Whenever the bridge is balanced and you apply a voltage across the bridge, the current through the intersecting region, that means the crossing points, which will be equal to 0. So this current will be equal to 0 ampere because the bridge is balanced. If it is not balanced, it is not 0. Okay. Now we will see the response only due to the current source.
The resistor, Doctor,
Sorry?
you changed the place of the voltage source with the resistor of I1 because they are parallel.
No, no, no. This is the voltage source. Let's say, see, this is C and D. Okay. So I can say this is my C and this is my D. Is it same? Okay. You can check it. Is it same or not? What happened to
Did you write something?
yes, actually I write something, now only it came because of some response of the software, I think so. There is some issue. Is it okay
That's okay.
now? Yes. Okay, you just
Now
observe
I can't
carefully. It
see
is
it.
same circuit. Okay. Now I will take only the voltage source. That means I will take the
We
current
can't
source. That
see
means
it.
make the voltage source.
We can
Can't
see
hear?
the
Okay, voltage source.
Doctor,
Now you can
the
see, I
screen
think so.
is disappear.
Screen disappear. Oh,
I cannot see, Doctor.
okay. There is some problem with the connection, I think.
also you're not visual to us.
Hello?
Yes, yes, yes. I can hear you. There is some problem with because of poor bandwidth, I think. That's why. Anyway, now you can see, I think so, right?
Yes.
Yes.
Is it okay now? Yeah, there is some problem with
okay
the
now.
connection. That's why. Okay.
Yes, sir.
So I will discuss this problem, and inshallah we will continue in the next class because the connection is not good. That's why. Okay. I will give you an homework. Anyway, now you see here we have another of this. You can see we have this network. I will make the voltage source equal to 0. Voltage source is 0 means what is the meaning? It is a short circuit, right?
Yes.
So I am going to draw
Short
it.
circuit.
This is 1 ampere, same, and you have, this is 1 ohm resistance, another 1 ohm resistance here, again 1 ohm resistance here. Okay, and you can see this is short circuit, and another part you can see here which is 1 ohm resistance, and you can see the current, and this current we will call I2. Okay, we will call I2. Now this is a short circuit. Now you can see it in a different way also. If it is a short circuit, I can draw it in a different way. This is 1 ampere. Okay, this is 1 ampere. Now you see here these two ends, that means this end and these two, they are short circuit. I think it is not appearing. There is some problem.
Yes, not appearing.
Yes.
Now it's
You can
okay.
see this 1 ohm, this, yes, these are parallel. Is it okay? This 1 ohm and 1 ohm are parallel. Is it okay?
Yes.
Can you agree with me? Yes, because this part is a short circuit.
There is 3 parts connected in one node. How could be parallel?
It's like this. Is it parallel or not between 2 points? I am talking about these 2 points. Is it parallel? Can I draw like this? The same thing? Is it same?
I
Yes,
think
because it's parallel.
Oh, it is not appearing. It is parallel. I'm sorry, it is not appearing because I'm writing here something and it is not appearing in the screen. That's a problem. Okay, so it is parallel. You can imagine, you can think it, and it is parallel, and it is 0.5 ohms. Okay, now you have something which is known as your 1 ohm here, and some current is flowing I2. Okay, some current is flowing I2. Now what about the other part? What about, is it parallel or not? These points and these points and these points, is it parallel? So I can write it between these 2 points. Is it parallel or not? It is parallel. You can see here, this is parallel, and this is, yes, this is 0.5 ohms. I will write like this. Is it okay? Can you imagine?
Yes.
Is it possible? Yes, it is parallel. That's, yes. If you just short circuit that path, then it is parallel. Now you see, you want to find I2, and you have 1 ampere. And what is the total resistance? These two are in series, and the total resistance is 1.5 ohms. Is it okay? So the current I2 is
Yes.
found out by using current division. Current division means you want to find I2, so you will take the main current and multiplied by the resistance of the other branch. The resistance of the other branch means it is 0.5 ohms divided by the total resistance. The total resistance is 0.5. Is it okay? Is it 1.5 plus 0.5 is the total resistance. So this is 1.5 and this is your 0.5, and this one is coming here. It is just the current division rule. You know this.
Yes, doctor.
Yes, doctor.
So you will get the current I2. Sorry, I will write it here. You will get the current I2 as 0.25 ampere. So the total current I is equal to I1 plus I2, which is equal to, you got I1 previously as 0 ampere. So 0 ampere plus 0.25 ampere. This is nothing but 0.25 ampere. Okay.
Doctor, when we had a voltage
Is it,
source, why we didn't consider it as parallel?
which one, which voltage source you are talking about?
In the previous, when we cancelled 1 ampere.
This one
Why
you're
we
saying
didn't,
here?
yes. Why we didn't consider
This one?
it as parallel? One with one and one with one.
Yes, what's the question? Because we are applying superposition theorem, we will consider only one source at a time.
No, not my question. I mean, when we first think, we cancel the 1 ampere source. Then we just apply
Yes.
1 volt source. Now, why we didn't consider 1 ohm and 1 ohm are parallel, as we did now?
Which? No, in that case, in the first case, actually, we got the, you see here, in the first case, we got the circuit in a different, in the second case, we got the circuit in another way. That's why. Okay. Because case, you can see this is a short circuit. And this short circuit will change everything. That's why we got in another way. The circuit is like this.
I didn't get how it could be parallel now, Doctor, with the short circuit.
Short circuit? What's the problem with you?
I didn't get how it can be parallel. 1 and 1 and also.
Okay, okay.
Because the connection part
Okay.
is same.
That's this one.
The
I will.
connection part.
Yes. I understood what is the question. The parallel connection. Okay. Now you see here. This is your circuit. This is 1 ohm. Okay. And this is 1 ohm. And this is 1 ohm. This is 1 ohm. Okay. And you know this is short circuit in the second case. Is it? You do you agree with me? This point? Yes. Now I will redraw the circuit in another way. I will use different color here. This part I will use different color. This is red color. Okay, I will use red color, and I will use another color here. This is, then it will be very clear to you. And this is a short circuit. This is a short circuit. Now you see, listen very carefully. I will draw this resistance here. This is 1 ohm. Okay, 1 ohm. And I will draw this resistance. I will draw this resistance. It is going like this and going here and coming back. That means I will draw like this and coming back. Is it okay? 1, 2, 3. That means I start from 1, I reach 2. 2 is after the resistance here. 2 and this is 3. Is it okay?
Yes, because of the short circuit, it can move.
Yes, because of the short circuit, you can move anywhere. Because short circuit means the resistance is 0. You see, you can move this guy, you can slide this and put it anywhere. You can just, this is a wire. You can put the wire like this, or you can put the wire like this. No issue. This is just a wire. You understood? A wire can, if you fold the wire like this, or if you fold the wire like this, no, both are same as electrical perspective. Whatever current flow here, the same current will flow here. Is it okay?
But I thought, Doctor, there is a node in the top right corner.
What those? There's a, what is a node? A node is, this is the point. A node, this is a node, and this is a node. And here, how many nodes are here in the second case? This is the first case and this is the second case. How many nodes are here?
1.
There's only one node. So you cannot consider this as a node. This is not a node. Not a node, you can say. Because a node is nothing but it is interconnection between two components. This is a node.
Yes.
You understood? Otherwise, if you consider this you can consider infinite node. This is not true. It is having only one point actually. You understood? So now I will say this I will remove. Use the different color. You have this resistance. You can see this is your point number 3. Okay. Point number 3. Okay. Point number 3. Now, how many are there between these 2 points. Point number 3, I will start from point number 3. In point number 3, I will consider first of all this resistance here. This is my resistance. And another resistance which is again going into point number 3. You can see it is going again into point number 3. It is starting from point number 3. So I start from point number 3. You can give some A, B, C, D. So A, B. Again, I have another thing, okay, which is going like this. A, B, C, D. And this is 1 ohm and this is 1 ohm. Is it okay?
Yes.
And from B, this is my connection from B. My connection from B. So this is my connection from B. And my connection here, it is going like this. It is going like this. This is 1 ohm. Now this is parallel. The resistance is 0.5. These two are
Right.
parallel. The resistance is 0.5. That's why we got like this. You understood?
Yes. Yes.
Inshallah, we will continue in the next class because the connection is very, very poor. That's why. Okay. Inshallah, we'll continue in the next class. Okay. Okay. Thank you. Assalamu alaikum warahmatullahi.
Thank you very much.
Alaikum assalam wa rahmatullah. Thank you very
Alaikum
much.
assalam wa rahmatullah. Goodbye.